Good morning, everyone. Sorry for the wait there. I did it again. I was sitting in my other chem classroom, Zoom room, all high and mighty, being like, where is everybody? They should be here. And I was in the wrong Zoom meeting, so shame on me. So we finished up gas laws last week. Done with that, check. You guys have, no joke, 2 chapters left. And then we're done. Then you have a final test and then you have your final. That's it. Isn't that exciting? So if you haven't started to register for spring fall classes, go ahead and do so. I don't think I'm on the schedule for a 151 for fall, which is the general chem, but if you're doing 130, usually my nurse techs, my vet techs and stuff like that, I will be teaching a couple sections of that. So keep an eye out. I always like having repeat students. And then we can meet in person too, because I'll be teaching in person if you are planning on coming to campus. So let's jump into the next chapter, which is solutions. My computer sounds like it's working really hard. Okay. Harder than it should be to open up a PowerPoint. All right, so chapter 13 and then also chapter 14, they're kind of like mixed together. Chapter 13 is talking about solutions, and then chapter 14 is going to be talking about acids and bases, and 99.9% of the time when you're dealing with an acid and base, it will be in a solution situation. So you may see some overlap here. For your information, tragedy in Lake Nyos in West Africa. So there was a lake in Africa that sat above an area with a lot of tectonic activity. So there were like geothermal vents and they were releasing a bunch of gas. Specifically in this area, it was releasing a bunch of CO2 gas. It was releasing this CO2 gas at the bottom of the lake, and the lake was relatively deep. So the water column sitting above that gas kept the gas in solution. It created sort of a pressurized situation, kind of like when you have a can of pop and it's closed, there's a pressure or a pressurized head that keeps all the little tiny dissolved bubbles in the solution. And so this lake had a bunch of dissolved CO2 in it. At some point, the pressure became so great and the lake got disturbed that the CO2 came out of solution. And this lake was sitting at the top of a hill. So the CO2 came out of solution and then it rolled down the hill because CO2 is less dense than oxygen or nitrogen in the atmosphere. So it rolled down the side of the hill. CO2 is normally relatively unharmful to humans, except if it's in high concentrations. So it ended up pretty much suffocating all the people and animals that lived at the bottom of this hill. And there were like, let's see, it said 1,700 people and 3,000 cattle that died because the CO2 covered the whole town. So now they degas the lake regularly, okay? So they have these pressure points where they can let CO2 out of the lake, and that doesn't happen. What does this have to do with solutions? Well, that lake was an example of a type of solution. It was a mixture, a homogeneous mixture of H2O water, probably with some other things, impurities in there, and then this dissolved gas, CO2. So a solution is any type of homogeneous mixture of 2 or more substances. Solutions are not necessarily just solids and liquids or liquids and liquids. They can be solids and liquids, liquids and gases, gases and solids, all sorts of different things. The ocean is an example of a solid dissolved in a liquid, specifically in water. Blood plasma that's running through your blood is a combination of a liquid with several solids. And then actually there's also some dissolved gases in there. That's how oxygen gets through your system. Lake Nyos was an example of liquid and gas. So all different types of solutions. Again, all of them, in this case, these two things are being mixed together and evenly mixed. So the concentration throughout the whole sample should be the same. If it's, you know, a 3 molar solution at the top, it should also be a 3 molar solution at the bottom. So a solution will have at least 2 components. You can have more than 2 components. You can have a solvent that's dissolving a couple different solutes, but for the sake of this section, usually you guys are just going to be dealing with 2 things. So the majority component, or whatever's doing the dissolving, is known as the solvent. The minority component, or what's ever being dissolved, is known as the solute. Usually if you're in a solid liquid solution, the liquid is the solvent and the solid would be the solute. Okay, so if we had salt water, the solvent is the water, the solute would be the salt. The solvent plus the solute, when you add these 2 things together, you get the solution. Okay. Because water is so abundant on Earth, and there's so many chemical reactions that are happening in water solutions, we have a specific name for water solutions known as aqueous solutions. All right, so there's a whole field with aqueous chemistry. There are other solvents used in the lab, and specifically, usually you have one thing that's polar to dissolve polar things, and then you have a non-polar solute to dissolve non-polar things. So here are some common polar solvents: water, acetone, methyl alcohol. You don't really have to have these memorized, but do know that likes dissolve likes. So if you want to dissolve something that's polar, you need to dissolve it with something polar. If I want to dissolve something non-polar, like remember those Lewis dot structures with the structures that were like really balanced and nice and everything was like really even, that would be a non-polar thing. You would have to have something that's also non-polar in order to dissolve it. Hexane is a really common one. So a formation of a solution from a dissolved, a lot of times it's a dissolved salt, but some sort of solid in water. What's happening? Well, you have your solid. So my solid is this thing down here. It has some sort of attraction, right? And this is known as the solute attraction. Solute because it's whatever's getting dissolved. So in this case, we're looking at sodium chloride. The sodium and the chlorine have some sort of attraction to them that has a certain amount of strength to it. When you put it in water, the water molecules, because they're polar, they have a negative side by the oxygen and a positive side by the hydrogen, that tugs on the solute. If that tug is strong enough or stronger than the solute-solute attraction, it can begin to pull this apart. So we've got our solute-solute attraction, we've got our solvent-solvent attraction, and then we've got the solute-solvent attraction. That's the water with whatever the solid is. If that tug is stronger than one of these tugs, it will start to pull it apart. So you can kind of think of it as like each of these NAs and Cls are popping off of the solid, and the chlorine is sort of surrounded by a buffering of hydrogens from the water, and the sodium is surrounded by a buffering of oxygen. So the sodium and the chlorines can't get back with each other. This attraction is greater than this attraction. Now, what happens if I start evaporating the water? If you evaporate water, you'll be left with the salt crystals behind because there's no more water to keep these two things away from each other, and they will just naturally come back together into solid form. So when you have a solution of sodium chloride, it will break apart into the ions. So it's not breaking apart into Na and Cl, it's breaking apart into Na plus and Cl minus. And these will be evenly dispersed throughout the water. Everything, all these different solids have a certain solubility. And the solubility is defined as the amount of the compound, usually it's in grams, that can dissolve in a specific amount of the liquid. So for instance, sodium chloride, and this is temperature dependent. So sodium chloride at 25 degrees Celsius, about 36 grams of sodium chloride can dissolve in 100 grams of water. If we were to say that the solution was saturated, that means that the amount of liquid that you have is holding the maximum amount. So a saturated solution would be 36 grams in 100 grams of water. An unsaturated solution would be anything that's less than the maximum amount. So there's really only one saturated point. There are many unsaturated solutions, right? I could be 1 gram of sodium chloride in 100 grams of water. I could be 2 grams. I could be 35.99 and haven't quite reached that 36 in 100 grams. As long as we're at 25, there will be a little bit of room to fill in. So it'll be considered unsaturated. In rare instances, you can make these things called supersaturated solutions. This is where you are holding more than the maximum amount. Usually you can make this happen if you heat up the water to a higher temperature, you pack a bunch of salt in it, and then you cool it down slowly. The system can hold like a little extra salt, but it's pretty unstable. If I was to drop like 1 grain of salt in there, a bunch of salt will precipitate out and it'll hit its new equilibrium of saturation at the new temperature. All right. So the solubility rules give us qualitative description of what will and won't dissolve. We've already gone over solubility rules, right? There are some things, there are some things that will dissolve in solution that actually don't break apart into any sort of ions. So usually salts, and when I say the word salt, I mean a general term for some sort of metal combined with a non-metal, or I mean an ionic compound. Salts usually will break apart into their ions if they're dissolving in solution. Molecular solids, so things that are 2 or more non-metals, when they dissolve, they are not actually breaking apart into ions. So a great example of that is table sugar. Here's the formula for table sugar. If you see there's no metal in this, this is all non-metals. So this means that the whole thing is covalently bonded together. So the packet or the molecule isn't going to break apart. It may break apart from its neighboring molecule, but the molecule as a whole isn't going to break apart. So if we look at an image here, on the left, this would be dissolved NaCl. Do you see how the NAs and the Cls broke apart into charged ions? Over here on the right is table sugar. Here are the little molecules. The molecules are no longer like connected to each other in a solid form, but the molecules stay as a packet. Why that's important? Because when you break apart into ions, you create what's known as an electrolyte solution. And an electrolyte solution contains dissolved ions. It is something that can allow for conductivity electricity. So I could run a current through an electrolyte solution, a non-electrolyte solution, for instance, sugar water. There's no charged particles hanging out in the solution. We have these stable whole molecules. So I can't run electricity through these things. So if you're looking to create an electrolyte solution at home, because you don't want to buy Gatorade or whatever, or you just need to up your electrolytes, you can make an electrolyte solution for your body out of table salt and water. You're not going to make it out of sugar. Okay, the sugar isn't going to give you the electrolytes you need. So how solubility varies with temperature, because I was telling you guys that solubility is affected by temperature. In general, if you are dealing with solids dissolved in liquids, okay, if it's gas and liquid, it's different. Solids dissolved in liquid will increase with increasing temperature. So on the y-axis here, I have solubility. How much salt can you dissolve? On the x-axis, I have temperature. As you increase the temperature, you increase the solubility. So the warmer the water is, the more salt you can dissolve. if you notice, table salt, NaCl, actually doesn't increase a whole lot. Its solubility doesn't increase a whole lot with temperature, but all these other salts, metals and non-metals, all these things, man, as soon as you increase that temperature, boom, you can pack like a bunch of salt in there. So warm water holds more salt. Colder water holds less salt. This temperature dependence or change in temperature is a way that we can actually purify substances. So a common way to purify like a solid, let's say we had table salt, is through this process known as recrystallization. So what you do is you take the material, the salt, whatever it is, you dissolve it in water, or usually you heat it up and dissolve it in the water. And then you allow the solution to cool. And as it cools, the cooled solution can't hold as much as the warm solution, so it will start to precipitate out the salt. If it cools slowly enough, the solid will form these really neat crystals, and the crystals will usually reject any of the impurities. So as it's recrystallizing, it won't put the impurities back in. It'll say, we don't want the impurities, and it'll form a purer substance. Have you ever bought rock candy for your kids or bought it for yourself? And it's like, it's like $6, for like one of those little sticks. You're buying a $6 stick of sugar because that's all it is. It's just table sugar. You can make rock candy at home. It's just table sugar that's been dissolved in water and cooled down and precipitated out, and you get this rock candy. It looks pretty, but it is just table sugar. So if we are looking at solutions of gases in water versus solids in water, the water at Lake Nyos, a can of soda pop, these are all examples where you have dissolved gases in liquid. Most liquids that are exposed to air in general contain some sort of dissolved gases. So how do fish breathe? They are able to, with their gills, filter oxygen out of the water. Where is that oxygen coming from? It's coming from the atmosphere above. So the atmosphere above is, there's some of that dissolved gas in the water. Our blood contains dissolved gases. Tap water contains a certain quantity of dissolved gases. We as human beings cannot extract that oxygen. I wouldn't recommend trying to extract oxygen out of water. We don't have gills, so we have to pull it directly from the air. Gases behave a little bit differently though than solids do as far as temperature is concerned. So when you have water, as you increase the temperature of the water, it is going to decrease the solubility of the gas. So they're inversely proportional. So a warmer water will hold less gas. How do you usually serve your pop or your beer or your Prosecco or champagne or whatever, your bubbly water? Usually serve it cold. Why do we serve it cold? Because I find it more refreshing, but also because a cold liquid will keep the carbonation, it will keep the gas in solution. A warm beer or a warm Coke is going to go flat much faster because that gas is going to release from the solution. It can't hold as much dissolved gas. Same thing as temperature of water increases, like let's say if you're dissolving a pot of water and it starts to, not the bubbling, but the little air, you see the little bubbles forming at the bottom, that's the gas in the water starting to release. This is a problem with temperature increasing, global temperature increasing. As we increase the temperature of our atmosphere and we increase the temperature of the oceans, well, the oceans can't hold quite as much oxygen. So we are actually seeing that there's a decrease in the quantity of oxygen in the atmosphere or in the ocean as well, which leads to fish dying and marine life dying. So here's our cold soda. Oh, look at that. So you can just tell that there's all the bubbles in there. It's going to be super crisp, right? This one over here, nice and warm. All of that fizz is coming out pretty readily. So if we increase the temperature, we decrease the amount of gas that can be dissolved. There's another law that affects how much dissolved gas you can have, and it's known as Henry's law. And it says the higher pressure, or the higher the pressure above the liquid, the more gas that can be dissolved in the liquid. Okay, so if the gas above is exerting a very low pressure, you're not going to find much dissolved gas. If the gas above the liquid is exerting a very high pressure, or you have a lot of gas particles, you would expect to see a lot of gas dissolved in solution. An example of where we see this, a closed can of pop that's pressurized, right? There's a pressurized head that's keeping all the gas bubbles dissolved. As soon as I open that can of pop, we move to this first box here where we have less gas sitting above. The gas in solution starts to dissolve out. There we go. Give me just 1 second. So we've got our closed can, CO2 under pressure, lots of CO2 particles. As soon as we release that pressure, we're going to see the bubbles come out of solution. Why do you start to see the bubbles when you open it? Well, one thing, when you dissolve something in a liquid, it's going to take the phase on of whatever that solvent is or the liquid is. So when you have a solid dissolving in a liquid, the final form of the solid is going to be aqueous, or it'll be dissolved in the liquid. It'll take on the liquid properties. Same thing with the CO2. When it's dissolved in the water, it sort of quote unquote disappears, right? But it's taking on the property of the liquid. So it will move and behave like a liquid until it comes out of solution, and then it'll return back to a gas. So, okay. So we've got our properties of different types of solutions. So the thing with the solution is that, you know, up until this point, you guys have really been dealing with just like compounds, which have had a specific chemical formula, right? You knew, you know, when you have CO2, you know, you have 1 carbon and 2 oxygens. With a solution, because it's a mixture of 2 things, I can change the proportionality, right? I can add more water, I can add more solvent, solute, whatever it happens to be. So because I can change the mixture's proportions, you can't do that with a chemical formula. Those are set in stone. But with a mixture, you can change the chemical proportions. You have to be able to represent what that proportionality is. And that's a concentration. So when I say, hey, the concentration of this solution is 14% mass, I'm saying that there are 14 grams in 100 grams of solution. So you as a writer or a chemist or whatever have to tell the reader what is the concentration of that solution. You know, you see concentrations all over the place in beauty products. You see them. I was like just doing a bunch of research on beauty products. I have no idea why I went down that rabbit hole last night, but there's like all these different products that have different percentages of vitamin C or salicylic acid. And it's really important as a consumer to know, hey, is my skin happy with 0.5% salicylic acid or 2% salicylic acid, right? That concentration can have a huge effect because it's like, how much of the active ingredient are you getting in a given sample? So one way that we can describe this is something called mass percent, or sometimes it's just called mass percent. Mass percent is the number of grams of the solute per 100 grams of solution. So if I say something has a 14% mass percent, that would be 14 grams of the solute in 100 grams of, and this is really important, 100 grams of solution, okay? Not 100 grams of the solvent, not this. A lot of times people think it's solute over solvent, like, oh, it's 14 grams of salt over 100 grams of water. No, it would be 14 grams of salt over 114 grams of water. Okay, so make sure you're using the solution mass on the bottom. And there's actually a picture of the equation here. Mass percent equals the mass of the solute divided by, and they actually put it in really basic words, the solute mass plus the solvent mass times 100 to get it in a percentage. This thing down here is also known as the mass of the solution. I'm going to say every single one until I get to the one I want, solution. So depending on the problem, they may give you the mass of the whole solution and you don't have to calculate it. Or they may give you the mass of the solute and the mass of the solvent. Just remember, when you're trying to get that denominator, you have to bring the two together to get the total mass of the solution. This is sometimes called parts per hundred. There's also ppms, which are parts per million. And we also have ppb, which is parts per billion. Parts per million and parts per billion is something that we use more so to talk about like trace concentrations of something. So you may hear, oh, there are 3.6 parts per million of mercury in our drinking water, or there are 2.5 parts per billion of perchlorate in our rainwater. When they're talking about part per million and part per billion, instead of saying, 1 out of 100, they're saying 1 out of a million or 1 out of a billion in these. We aren't going to do a whole lot of, we're not really going to do anything with part per million and part per billion, but just useful to see how that relates to mass percent. If we are given mass percent and I give you like grams of solution and I want to know or grams of solution, I want to know grams of solute, we can actually use the mass percent as a conversion factor because again, mass percent is equivalent to or equal to grams of the solute over 100 grams of solution. So an example of this. If I say that a solution is 36% NaCl, that's the same thing as saying I have 36 grams of NaCl in 100 grams of solution. These two things are equivalent to each other. This one is a little bit more useful if you want to plug it into like dimensional analysis, because you can either use it this way or you can flip it and use it the other way. But there's grams of solution and there's grams of the solute. So you can jump back and forth between solution and solute pretty quickly. Let's say we had a solution of 11.5% KNO3. Write a conversion factor for that. And just assume that this is all aqueous happening in water. It shouldn't. Okay, so hopefully, you can see that this translates to this. If we were given a different value here of 11.5%, that would be like saying I have 11.5 grams of the KNO3 in 100 grams of solution. So know that you can always convert these back and forth, this if you like to set it up with dimensional analysis. So let's do a problem. I don't particularly like the problem that they give us here. I feel like it's more complicated than it needs to be. So I'm gonna give you one. What is the mass percent of solution when is 22.5 grams of KCl in 100 grams of H2O. Give you all 2 minutes for it. Not super complicated. Okay, so we're doing a, sorry, splattered coffee all over my screen and it's a touch screen. So we've got something that's asking about mass percent. So, you know, it's always helpful to say, okay, if we're talking about mass percent, let's just write the equation out so I don't forget anything. It's going to be mass of the solute over mass of solution, underline that, times 100. So do I have the mass of the solute? That's the thing that's getting dissolved. Yes, it is 22.5 grams of KCl. The mass of the solution. So what people I see happen here a lot, especially when it's like set at 100, is they go, oh, it's over 100, so it must be 22.5%. But that is only the solvent. I need to take the grams of the HCl, or I'm sorry, the H2O, and I need to add it to the 22.5 grams of the KCl. That will give me the total solution. What's going on here? Pen is not working for me right now. So 22.5 divided by 122.5. And that does make a difference, because if we had just taken the solute divided by the solvent, just this here, that would have been 22.5%. Oh, I'm sorry. I always do that, right? Writing that multiplied by 100. But we need to add the solute to it. So we should get 18.4%. And I could write this a different way. I could say, hey, for this given solution, there are going to be 18.4 grams of the KCl in every 100 grams of solution. Questions on that? No? All right. Let's do another one, set up in a little bit of a different way. So how many grams of solute, how many grams of, I'm not just going to say solute, how many grams of CaCO3 are in a 9.6% if you have 85.4 grams of the solution. Sorry, that was written sort of wonky, but how many grams of KCO3 are in a 9.6% solution if you have 85.4 grams of the solution? And there are kind of two different ways you can go about this. You can either plug it into the equation, or you can do it in dimensional analysis using the mass percent written as a conversion factor. I will show you guys both of them in about 2 minutes. Okay, so we can plug and chug it into the equation, which tells us that mass percent is equal to mass of solute over mass of solution times 100, right? So what do we have? We have mass percent, it's 9.6. Mass of solute is this thing. The solute is whatever's getting dissolved. So we're trying to find that, grams of CaCO3. Do we know the solution mass? Yeah, we have it here, 85.4 grams. And we multiply this whole thing by 100. So we just want to isolate for this. So we're going to take our 9.6, we're going to divide each side by 100, right? And then we're going to multiply each side by this 85.4, by 85.4. And you should get, this whole thing is equal to 8.2 grams of CaCO3. That's one way to do it, is plug and chug. Another way, which will get you the same answer, is to set it up in dimensional analysis where we say, hey, my mass percent was 9.6, right? 9.6, yeah. That's the same thing as saying 9.6 grams of the solute, which is CaCO3, in every 100 grams of solution. You guys good with that? Where that came from? Just by definition of what a mass percent is. Okay. So we start with our given, which was that we had 85.4 grams of the solution. And I use this as a conversion factor. I want solution on the bottom, so I'm just going to keep it the way it's written. 100 grams of the solution will yield 9.6 grams of the CaCO3. The grams of solution will cancel out and you'll be left with grams of CaCO3. Look at what you're doing. You're taking that 85.4, you're dividing it by 100, and you're multiplying it by 9.6. That's the same thing you did right here. All right, so you will get the same answer. People who are really like dimensional analysis, go with the second option. People who are like, ugh, dimensional analysis, no way. I like to plug and chug. Use the first way. I don't care which way you do it, just as long as you can get the correct answer. All right, but know that there are two options with that. So are there some other ways to talk about concentrations? There are. It looks like it doesn't go into mass volume percent. So I'm going to write that over here because you do see it in the labs. So another way to explain concentration is, well, one is called volume percent. That's the volume of the solute divided by the volume of the solution times 100. So we've got mass percent, we've got volume percent. Then we have this funky thing called mass volume percent. This is going to be grams of solute over milliliters of solution times 100. This one here, the volume percent, that could be in milliliters and milliliters or liters and liters, as long as the units are the same. Okay, that one you're fine, keeping them just consistent units. This one though, this mass volume percent, it's very strict about what it wants the units to be. It needs to be in gram on the top and milliliter on the bottom. It's a really funky sort of way to represent concentration, but that's another option. I'm not going to go over those two in the slides, but you might see them pop up in the homework and in the labs. Okay, so how you plug and chug, it's the same thing with mass percent. You're just using volumes or masses and volumes, right? But one I do want to talk about and we'll work on is really, I would say, one of the most important concentrations or units for concentration, which is this thing called molarity. This is how most concentrations are represented, especially in like a lab setting. If we were meeting in person, there would be, you know, chemicals out with different concentrations, and they would always be given to you in molarity. So molarity's unit is a capital M. It is not a lowercase m, that is the meter. It is not MOL, that is the mole. Molarity is related to moles. It is not the same thing as moles, okay? Moles is an amount. Molarity is an amount per volume, all right? So molarity equals moles divided by liters. The top thing needs to be in moles. The bottom thing needs to be in liters. So know that if you're given a top value of grams, or if you're in the problem, if you're given grams, you have to convert it to moles. If you're given milliliters, you have to convert it into liters. This equation will not work if it is not in moles and liters. Also note that the top one is talking about solute and the bottom one, again, is talking about the entire solution. So it's not liters of just the solvent, it is liters of solution. One way to see this is when you are making a stock solution. So let's say I wanted to make, we were running an experiment and I needed it to be a 1 molar solution. Sometimes you'll see the word molar. That is the same thing as molarity. Okay, molar and molarity equal each other. Also same thing, big M. So if I wanted to make a 1 molar solution, well, let's go back to the units. Or I'm sorry, let's go back to the previous slide here where we can see the equation. So what is molarity? Molarity equals moles over liter. Well, if I've got a 1 molar solution, isn't that the same thing as saying 1 mole of solute over 1 liter of solution? It is. It's the same thing. It's mole per liter. Okay, these two things are equivalent. So if I want to make a 1 molar solution, I need 1 mole of salt, and 1 mole of salt is roughly 58.44 grams. And I need to dilute it to a liter solution. First, you add the salt, then you add enough water to bring it to a liter. Why wouldn't I fill it with water first? If I filled it with water first to a liter, and then I add the salt, how big is my solution volume going to be? It'll be something greater than a liter. Then your concentration will be off, okay? So you always add the solid first, and then you dilute it to whatever that final volume is that you want. What if we had something that was not just 1 molar, but we had something like 6 molar? It's a pretty strong, so let's say we had a 6 molar HCl solution. That is the same thing, that's like saying the same thing as 6 moles of hydrochloric acid, HCl, in every 1 liter of solution. The number, if you're converting it into a double unit dimensional analysis conversion factor, the number 6 here goes on the top. It's always a per liter. The 1 will go on the bottom. So let's say we had a 3 molar HCl solution. That is half as concentrated. That means that you're going to get 3 moles of HCl in every 1 liter of solution. So you're always comparing it to a liter. Yeah, I mean, just for fun, 2.33 molar HCl, very specific concentration. The number always goes with the top value, 2.33 moles of the hydrochloric acid in every 1 liter of solution. So these things here, molarity, it's not the same thing as moles, but it's related to moles. As the number of moles goes up, your molarity will go up as well, right? As long as it's the number of moles is going up over a given volume, a given amount of solution. So I'm going to give you a problem here. Super simple, just to plug and chug for a minute. What is the molarity if you dissolve 8.5 moles of NaCl to make a final solution of 25 liters? So what is the molarity if you dissolve 8.5 moles of NaCl to make a final solution of 25 liters? So nothing, revolutionary here. It's just molarity equals moles over liter. Anytime you see the word molarity, I'd just write that out. See if you can plug some things in. Do we have moles? Oh yeah, we've got it all ready for us, 8.5. Do I have the volume in liters? Yeah, 25 liters, moles per liter. When I divide them out, I get 0.34 and the unit on this would be big M. Or I could also write this as 0.34 moles per liter, per every 1 liter. Either of those work. This one is a little bit better if you're trying to plug it into dimensional analysis. How often does a problem give you moles? Not very often. What do they usually give you things in? Grams. So if they give you grams, you need to convert to moles. So let's do that. I think the slides actually have an example, so we'll just use theirs. Okay, calculate the molarity of a solution by putting 15.5 grams of NaCl into a beaker and adding water to make 1.50 liters of NaCl solution. Similar, very, very similar problem to the last one, just an added step there. All right. I'll give you guys a quick help here, just for time's sake. So the molar mass of sodium chloride is 58.44. I think that's close enough. Yeah, 58.44. Okay, so just use that molar mass. Okay, so in this problem, you just have the added step in that you're given the amount of the solute, but it's given to you in grams. It already gives you the volume in liters. So remember, molarity equals moles over liters. We have grams, we need to get our grams into moles. So first, converting NaCl gram into mole, we divide by the molar mass and you should get 0.2652 moles of NaCl. Then once you've got it into moles, you can plug it into that molarity equation and you're good to go. In this case, we get 0.177 capital M molarity. Okay, let's do one moving in the other direction. So how many grams of FeCO3 are in 16.4 grams of a, sorry, no, rewind. How many grams of FeCO3 are in 16.4 liters of a 6 molar solution. How many grams of FeCO3, which is going to be your solute, are in 16.4 liters of a 6 molar solution? And I'll make that 6.0 so we can have 0, so we can have 3 sig figs. So there are 2 different ways you can plug and chug it into the equation, or if you like the dimensional analysis, you can set it up by converting this into a conversion factor. Either way works. I'll give you guys about 3 minutes for that one. Okay, so in this one, there's 2 different ways that we can solve it. We can plug it into the equation, which is, molarity equals moles over liter. I find this one the easiest to do for this problem. So we have moles, which is 6.00. Or I'm sorry, we have molarity, which is 6.00. We don't know moles, but we do have the volume, which is 16.4 liters. If I figure out moles, then I can figure out grams, right? So I'm going to take my moles, or I'm going to take my molarity and multiply it by my volume. So 6 times the 16.4 gives me a mole value, moles of 98.4 moles, specifically of FeCO3. Now the problem wants it in grams, so the last step is just to sorry, give me just a sec. This thing is freezing up on me. So we want to convert this by using the molar mass. So 1 mole of FeCO3 is 115.85 grams of FeCO3. Sorry, the internet is working a little slow here. So we're going to multiply those two together because we want to get rid of moles. 98.4 times the 115.85. End up with a relatively large number of 11,399 grams of FeCO3, and we only want 3 sig figs, so 1, 2, 3. So I'm going to go with 11,400 grams of FeCO3. Now what you guys got? No. No, okay.
So I'm confused about where you go from 6M to how many moles are in 16.4 liters. Can you back up to that and explain it?
Yeah. So this is, so right here we have an equation with 3 variables, right? So when you have an equation with 3 variables, I can give you 2 of them and you solve for the third. Does that make sense, Elizabeth?
I messed up there too. I've divided. I put multiplication instead of an equal sign.
You put a multiplication here?
Yeah.
Okay. Okay. No worries. Yeah. So this is a very basic 1, 2, 3 equation. So if I want to figure out something about grams, the only thing in this equation that could get me to grams would be the mole, right? Mole and gram are sort of interchangeable. I have the information on the other 2 variables, so I just literally plug it in. If I want to get moles by itself, what do I need to do? I need to multiply this side by 16.4 liters so that the 16.4 goes away, and I multiply this side by 16.4 liters. Remember, the unit for molarity is mole over liter, right? Those 2 things are the same. So liter and liter will cancel and you'll be left with just a unit of a mole. So you're just multiplying them 2 together. Does that make a little more sense, Elizabeth? No.
So wait a minute. So what we're trying to figure out here is like a ratio rather. Is that what I'm missing? Because it's not. Because we're looking for the number of moles in 16.4 liters. Yeah, okay. Yeah, I think I figured that out. Okay.
Yeah, so the problem could be a variety of things. It could give you moles in liters and you solve for molarity. It could give you molarity in moles and you solve for liters. It could give you molarity in liters like in this one and you have to solve for moles or grams. So it's just a 3 variable equation. Just like back in the day where we had like Q equals MCAT, right? And you were given 3 of the 4 variables and you solve for the 4th. There is another way to do this. You could do it dimensional analysis style, which I think actually makes it more complicated. But in that instance, for dimensional analysis, if you have the 6.00 molarity, right, that's the same thing as saying 6.00 moles in every 1 liter. Those two things are the same thing. So I start with my given information, which is, what did we say? 16.4 liters. 16.4 liters. We multiply it by this thing, which is the 6.00 moles in every 1 liter. The liters cancel and we'll be left with units of moles. So we're multiplying the 2, which gives us the 98.4 moles of the FeCO3. And then from there we convert. So this, we sort of are back at this step.
Okay, yeah, I think I just needed you to like stick that extra step in there for my brain to wrap around that.
Okay, yeah, so you can do it either way. You can do it as dimensional analysis, like here where you have the conversion factors, or you can just plug it into the equation. Some people like the dimensional analysis better. Let's see where we are time-wise. We've got a little bit more time left. So let's just do another one of these just to really make sure we've got it. So 3.7 grams of KCl are dissolved. Can't see what I'm writing. Make a 8.5 molar solution. What is the volume of the okay, so 3.7 grams of KCl are dissolved to make an 8.5 molar solution. What is the volume of the final solution? So I flipped out a little bit which ones you need to solve for and which ones are given. So we've got just 4 minutes left in class, so I'll give you 2 minutes to try and chip away at this. Let me get you the molar mass on KCl so you don't have to worry about that. KCl molar mass is equal to 74.55 grams per mole. Okay, so just for time's sake, I'm going to hop into this. So we have an amount of mass, and we know the molarity. Mass isn't in this equation, but this is almost as good as moles if we just convert it to moles, right? So 3.7 grams of KCl. If I want to convert that into moles, 1 mole of KCl, and I gave it to you right here, was that 74.55 grams of KCl. So we need to divide it by its molar mass. We get a small amount, 0.0496 moles of the KCl. Now I can plug this into the equation, right? I have the mole value and I have my molarity right here. So I have that 8.5 big M is equal to 0.0496 moles of KCl divided by my volume in liters. Now you need to get liters by itself. So I'm going to actually move, since liters is on the bottom of the fraction bar, I'm going to multiply this by liter so that it cancels. And then I'm going to multiply this side by liter. Then I'm going to move the 8.5 over. So I'm going to divide this by 8.5 and divide this side by 8.5. So I should be taking my 0.0496 and dividing it by the 8.5. And I end up with a volume of 0.00584 liters. It's a small amount, small volume, but it's a small number of moles. It's not a very big gram amount. If you pitfalled into this, where you had the equation 8.5, 0.0496 over the liters, and you were like, okay, this was moles. I'm gonna divide this side by this, right? 0.0496, and you divide this by 0.0496 for those to cancel. You have solved for, not liters, you've solved for 1 over liters, right? 1 over liters. So then you need to take the inverse of this and the inverse of this. So if you didn't get this number, that's why that happened. That's why I moved the liter over here and divided this by this. Okay, that's just isolating variable stuff. So we will stop there. We'll continue on with solutions on Wednesday. We are getting pretty close to the end of the semester, so just staying on top of stuff. Message me if you are late on a lab here or there, or have any questions about your grades, and try and work some of that stuff out. Registration opens on Friday. So I will see you guys next time. If you have a question, general question, just throw it out there. If you have a personal question, stay around and we can chat privately. Have a nice rest of your day. Bye, everyone.